first shared their stories in caves, connected art, nature, and science, led us toward new horizons. Who thought to capture motion, spark an engine to life, turn television into a playground? Every day, you create the playful, the functional, and the unexpected. You break down walls and take us to astonishing places. Tell stories, leap borders, and create beauty for tomorrow. Because at Unity, we believe the world is a better place with more creators in it, where everyone has a chance to shape the world.
Hey everyone, welcome to our weekly Unity South APAC webinar series. I'm Sarah from the marketing team, and on the call we have Jenny, who's also from marketing, and our few engineering team, Hector, Sean, and Tech.
Hi,
So a big
Sarah, how are
welcome
you?
to everyone. Hello, good. So a big welcome to everyone joining us from all over the region, from India, Pakistan, Singapore, Philippines, New Zealand. Very nice to have you live with us today. Quick reminders about interaction during the webinar. So please put your questions into the Q&A box, not the chat box. The chat box is only for materials and resources that we will share with you. And also do not use the raise hand function. The total duration for today's session will be around 90 minutes. So as always, we do a lucky draw where one lucky registered person who fills in our survey form at the end of the webinar will walk away with a Unity Sweat Pack. And we'll share that survey link at the end of the session. So in case you're joining us live from another streaming platform like YouTube, you can scan this QR code over here and register to be eligible for the draw. But if you're already joining from Zoom, there's no need to do so because you would be registered already. So some of our past winners, congratulations to all of you. And once again, the QR code is here. I'll leave it up for another few seconds. Oh, and also we're also giving away a sweat pack to the best question for today's session. So, leave your questions in a Q&A box as we go along the session, and our few engineer team are all live right now to answer your questions. All right, so we are at the end of our Building an Arcade Racer series. Huge thank you to everyone for joining us through this series. You can find past recordings on our SAPAC webinar page in case you missed anything. And as always, we pre-recorded today's session last night to optimize quality. So our speaker, as you've heard, Hector is online, and the rest of the team is online as well to answer your questions. So with that, take it away.
Hello everyone, welcome. My name is Hector. I am a field engineer at Unity based in Singapore, and today I will be guiding you on today's webinar, Building an Arcade Racer. This is the part 5 of a series, and today we will be looking at machine learning agents. Okay, first I'll give you an overview of the ML Agents Toolkit. We will have a look at how to install it and learn about its key components. We need to be able to set up a training environment in order to be able to train an agent to drive our car in the arcade racer game. Once an agent goes through training, all the experience accumulated by trial and error is stored as a model, which can then be used as a brain driving the decisions of our NPC in our game, for example in the case of computer-controlled opponents. Finally, there will be some time to answer questions at the end of the presentation. The Unity Machine Learning Agents Toolkit, ML Agents, It's an open source project that enables games and simulations to serve as environments for training intelligent agents. It provides an implementation based on PyTorch of state-of-the-art algorithms to enable developers to easily train intelligent agents. Researchers can also use the provided Python API to train agents using reinforcement learning and imitation learning, among other methods. These trained agents can be used for multiple purposes, including controlling NPCs, automated testing of game builds, or for evaluating different game design decisions during development. The ML Agents Toolkit is both beneficial for game developers as well as for AI researchers, as it provides a central platform where advances in artificial intelligence can be evaluated by the wider research and game developer communities. You can find this open source project on GitHub. Machine learning is a subset of artificial intelligence that provides systems the ability to learn on their own and improve from experience without being programmed externally. It focuses on learning patterns from data. The three main classes of machine learning algorithms are unsupervised learning, supervised learning, and reinforcement learning. Each class of algorithm learns from different types of data. The first two are useful in cases, for example, of image classifiers, which can be used in computer vision. But the most relevant learning algorithm for our ML Agents Toolkit is reinforcement learning. Reinforcement learning can be viewed as a form of learning for sequential decision making that is commonly associated with controlling an agent. More specifically, the goal of reinforcement learning is to learn a policy, which is essentially a mapping from observations to actions. An observation is what an agent can measure from its environment, and an action is a change to the configuration of the agent. In the case of our arcade racer, we are going to train a driver agent, so we need to make observations such as the current position, current speed, relative direction. And then our agent needs to take actions such as steer, decide whether they need to accelerate or brake. The last remaining piece of the reinforcement learning task is the reward signal. Our driver agent is trained to learn a policy that maximizes its overall rewards. When training an agent to be a great driver, we provide it with rewards positive and negative, indicating how well it's driving. Please note that an agent doesn't know how to drive around the track before it's trained. It learns the objectives because it receives a large positive reward when it does well and a small negative reward when it makes mistakes. Such as driving out of the track, for example, or crashing into obstacles, or going into the wrong direction. Learning a policy usually requires many trials and iterative policy updates. More specifically, the agent is made to drive several situations, and over time it will learn the optimal policy which allows it to drive more effectively. Because of Unity's ability to simulate physics, it serves as a perfect training ground for learning these behaviors. So it's natural to explore how we can train behaviors within Unity using reinforcement learning, and it's precisely what the ML Agents Toolkit offers. There are three main parts to using ML agents. First, you need to integrate ML Agents Toolkit into your project and set up the training environment. Then we can run training sessions which in time generate a neural network file that we call a brain. This brain is a small file size neural network that can be embedded into your games and deployed to your Unity application. The ML Agents Toolkit includes an SDK that enables you to transform any scene into a learning environment by defining the agents and their behaviors. How you set up the Unity scene to serve as a learning environment really depends on your goal. You may be trying to solve a specific reinforcement learning problem of limited scope, in which case you can use the same scene for both training and for testing trained agents. Or you may want to be training agents to operate in a complex game or simulation. In this case, it might be more efficient and practical to create a purpose-built training scene. So there's also a Python low-level API which contains low-level Python interface for interacting with and manipulating a learning environment. Please note that unlike the learning environment, the Python API is not part of Unity, but lives outside and communicates with Unity through the communicator. This API is contained in a dedicated Python package and is used by the Python training process to communicate with and control the academy during training. The external communicator, which connects the learning environment with the Python low-level API, which lives in the learning environment. That's part of Unity. And finally, the Python trainer, which contains all the machine learning algorithms that enable training agents. The algorithms are implemented in Python and are part of their own ML Agents Python package. The package exposes a single command line utility, ML Agents-learn, that supports all the training methods. One aspect of the learning algorithms is that they all involve a training phase and an inference phase. The training phase involves building a model using provided data, while the inference phase involves applying the model to new previously unseen new data. More specifically, the training phase learns the optimal policy through guided trials, and the inference phase, the agent observes and takes actions in the wild using its learned policy. You can see in this diagram right here how the agent A1 and A2 are applying a behavior through the communicator and doing a part of what we call the training exercise. And they go through the communicator up to the Python API to the trainer. And then they get decisions sent back to the agents to take and try and see how they perform in the environment. The example of Agent C1 is actually performing another different behavior, but this one is based on inference. And this is self-contained within Unity based on an already trained model. And finally, the one on the right, the Agent D1, is also following a behavior, but following a heuristic approach. And heuristic, in cases of testing agents, usually relies on human input. So we can configure an agent to be controlled by the keyboard, for example, and have a user play. And that would be heuristic approach, but it could also be controlled by a coded algorithm. Let's have a look at how to integrate ML Agents Toolkit into the editor and install the Python and the required modules into a new project. Okay, the first thing we're going to do is create a new project. I'm calling it my ML projects. Okay, so here we are inside Unity. So the first thing that we need to do is go to the package manager. So let's go there, package manager. It's in a different window right here. It's fetching the packages and features. So things that we need to do is change this to download from a Unity registry. Show me a list of packages from the Unity registry. Then we're going to scroll down until we find ML Agents. And that is the package that we need to install in the Unity side. So let's go ahead and do that right now. Click on Install button and let it work. It's going to install all the Unity side elements for machine learning agents. All right, so now that we install the package from the package manager, we can confirm that we have it by selecting any game object and going into add component, and there should be a new option called ML Agents. And if you click there, you can see all the scripts corresponding to the package that we just installed. Okay, that's great. So now let's move on to installing the Python side of the ML Agents Toolkit. Okay, first thing we need to do is install the Python on our system. So in order to do so, here's the instructions, the installation instructions for the Python side of the ML Agents Toolkit. So in this, if you search for ML Agents installation, you will find this website. And here is from the GitHub, from the open source project, all the information of how we can go about and install. I have in my system already installed 3.6, Python 3.6, but if you don't have it, you can go to the Python website and find it how to download it. I think I have that open right here. So this is what it looks like. I search for Python 3.6, which is the version I have currently installed on my system. And you can go to the download section, download and install it, and you will have it on your system. Okay, now to confirm that you installed Python correctly, you can open a command prompt in Windows or a terminal on Mac and type Python. And then you will see here I have my version installed 3.6 correctly showing, and this means that my Python is installed correctly on my system. Okay, next up, I can navigate to the project folder in Unity. In my case, I have it in here in my ML Agents project. And in the Explorer, I can just type CMD here to open a command prompt at that location, bring in the window. And now what we need to do is create a virtual environment. In order to create the virtual environment, we can go back to the documentation page and search for virtual environment. And here there's a guide on how to create a virtual environment. You will simply create a, so for different platforms, Mac, Ubuntu, Windows. So in my case, all I need to do is find this line, sample environment, and go back to my command line. So I have the command line right here. I'm gonna paste this, show you what it says. So it's Python. Created is going to run a module, a virtual environment, Python environments. Maybe I just call it my environment. I press enter. That's gonna take a second. And once it's done, I can look at the Windows Explorer, and in the project window where I have my Unity project, you see a new folder called my.env that was created with this line right here. It's like setting up a folder with a lot of default libraries and packages that are going to be pertinent to my project that I'm going to install next, which is ML Agents. Okay, once that we created the virtual environment, we need to activate it in order to start using it. So in order to do so, you can go back to where we were just now. There is a new folder created, my environment. So my environment /scripts, and then there is an activate batch file. So if we run that, you can see that now I'm running in the virtual environment of Python. And here's where I can install my ML Agents package. If we go back to the instructions where we come from, right here, it says right here that before we install ML Agents package, we need to install PyTorch. PyTorch is a library that ML Agents relies on to do all the artificial intelligence machine learning training. So we need to install that by calling this line right here. I'm running in my virtual environment, as you can see here. I'm going to paste that line and hit enter. So this is like a package manager, similar to the Unity package manager or NPM for Node.js. Going to take a while and fetch the necessary files and download into my system. I've downloaded this before in another virtual environment, and it's actually quite a long download. When I installed the first time, the download was about 2 gigabytes. Oh, and now after installing PyTorch, you might get this warning, this message. It says the package manager is running an older version. There's a newer available. So this is a good thing, actually necessary, because I tried to install ML Agents with the version 18 of the package manager and it failed. So we need to upgrade the package manager. So I'm going to copy this line and paste it. This will upgrade the package manager to the latest version. And now that the package manager is up to date, we can go ahead and install the ML Agents package. Go back to the installation documentation and see how that is done by calling this line right here. Going back to the command line and paste that line. Let me move this a bit higher and press enter. And that is installing ML agents. And that's it. So now we completely install the ML agents package. So that means that we can run ML agents -learn and --help. And yeah, we see the package is ready to be used. And here we'll show us the help on how to use it to start training in Unity. And that is integrating ML Agents Toolkit. Let's take a moment to see if there are any questions so far. Hello, so let's have a look at the questions and answers box right now. I'm gonna go through some of the questions that have been coming in that I marked to answer live. So there's one that says, how can I input Python into Unity? And what's the difference if I use Java? So the ML Agents Toolkit is designed to work with these two parts, the C# components within Unity, plus the Python packages. So there is no use of or version of ML Agent Toolkits that work with Java. The second question says, what more can I do with ML agents? Well, this is a very, very big question. You can do pretty much anything you want. And the idea of this presentation is to try to use ML agents to train the agent to drive in our car. But you can also, we will open the door for you to explore all the possibilities for ML agents. So towards the end of the presentation, there is some information about different environments and different types of training scenarios that you can explore for your agents. So please stay tuned and you will find more information about that. With ML agents support will ML agents support other neural network types in the future, or what path should I take if I want to build a neural network that is something like a language model? Okay, my understanding is that it does support different models, but right now the format that it works with is ONNX, Open Neural Network Exchange format, which I understand is a standard for this type of for neural networks. So if your whatever other program you're working with can convert from ONNX, then it should be fine, or it should be something that the team will be working on and give updates. So I would just look up for the ML Agents GitHub open source project and they'll have news and probably there's even updates on what are the new models supported or how it works. Then let's move on to another question. Okay, one more right here. I do not have a powerful machine. Will my PC be able to handle it? Then there's no dedicated GPU. Yes, we'll get to this later on, but for you to understand that the trained models are compiled into a very small file size file that represents the trained model. And this is interpreted by Unity Inference engine, which is built into the Unity as part of the ML Agents Toolkit packages. This is designed and optimized to running on multiple platforms and to take advantage of different devices. So if there's a scenario where the models can be resolved using GPU, they will be using compute shaders, but also can run on CPU. And it doesn't require a lot of processing power. So if the thing that you need to understand is training the model takes time and effort, but resolving or doing the inference on the trained model, that's quick. And it's also quick by the Unity standards compared to other inference methods that are out there. Okay. Let's see if there's any more questions. I mean, there's a lot of questions coming in, but let's move on with the presentation first, and then I'll see if I can address them in the questions and answers box. Okay, we'll have another checkpoint later on to answer more questions. Let's continue with the presentation. Now that we have integrated the toolkit and the Python modules required, let's have a look at how to perform the actual training for the agents. Okay, we are back into our Racer project. where we have already installed the ML agent package. So let's have a quick look to confirm. If I scroll down to ML agents right there, this is the version I am currently using, 201. Again, to confirm, Unity version is 2021-3.1, as we have been using throughout this series. Okay, I'm gonna close the package manager. And then the first thing in order to train is we need to define what an agent is. So in our case, the agent is going to be in charge of controlling the aspects of driving the car. So we talked about what the different elements of an agent are. The agent will take observations from the environment. So we need to define what those are. And it's up to us to give it meaningful observations. So remember what we talked about earlier about what an agent is. In reinforcement training, an agent takes observations of the environment, and then it will take actions based on some decisions that it makes. And as part of these decisions that it made, some things might happen in the environment. And depending on what is the rules that we define for our particular agent and how we train it, we're going to be able to grant a reward, which could be positive or negative. So if it's a negative, it's a penalty. And that is the basics of reinforcement training. So in the case of our car, we need to define what are going to be the observations. So we can say that the observations in this case, what I want to train my car in first is very simple. I put him in this very simplified environment where we have a sphere that I'm going to set as a target. And I want the car to be able to steer towards the sphere. So to steer towards the target. And no matter where the target is located, I want the car to always try to steer and try to hit it. This way I can later use it to drive around the circuit. This is one very simple basic task that I want to try on first. So how will we achieve that? I have already in my car here, I created a driver agent. So in my hierarchy right here, you see I have the steering target, which is the sphere, the ANZSEA object, which is the car that we have been using in our project, and driver agent is a new game object. Let's have a look at the inspector for this one. Let's move myself out of the way. Here we have a steer to target agent that I created with some custom properties, car and collider, player input, and then some properties that I want to expose in the inspector here, like heading, which is where is the car heading towards the target or not. And also we have two positions, two vectors, one vector for defining the car forward, just to monitor it here in the inspector, and another one to see what is the vector to the target. This is so that I can see it in the inspector, and also like we can visualize it later. Let's have a look at this agent script. So when I open the script in Visual Studio, you can see that this is just a normal mono behavior that I created. And then instead of having it inherit from mono behavior, it will inherit from agent. Agent lives in the Unity.mlagents namespace. And by doing so, I can override some functions that are part of this class. So if we look at the definition of this type, you can see that the interface that it implements and the virtual methods that we can override. The things that are important for us here are going to be collect observations that we're going to be using. Today on actions received, which is called by a decision taken based on the observations. And finally, there's one more that we use. There's heuristic that we use only when we are testing the agent and see if it's configured correctly. And also we have another one called set reward, of course. Set reward we're going to be using to define the positive and negative rewards. And there's also one more that we can implement, which is we can call end episode when we are done on an episode. say the character made a mistake or actually reached the objective that we wanted and got the reward. Then we can end the episode and start a new one. And there's one more that we can override, which is on episode begin. So this one is called when we end the episode, everything needs to be reset back to where it was, or in a new testing condition. And then all this reset code must belong in the on episode begin. So let's have a look at how that's done in the actual class. If I go back to steer to target agent, you will see a few things here. Let's start by going to the collect observations. Collect observations right here. So by overriding this virtual function, collect observations, it takes a vector sensor type object. And what we can do with it is call add observation to the sensor object. And what we need to add here is the things that are interesting for our card to understand the world and the environment. We'll try to keep it simple and basic for now. So all I'm passing is the car local position, which is a vector 3. And the next observation that I'm going to pass is the target. So I have a collider reference, so I resolve the transform out of that and then also get the local position. So I'm going to get the position of both where the car is at any point and where's the target at any point. Every iteration that we call for collect observations. So another thing that I'm interested in learning about is the heading. So for heading, I'm using this dot product for the vector of the car forward and the vector to target. So first I calculate the vector to target depending on where the character is. There's a vector from the car to the target. So I calculate that, and then there's also the heading of the car. So by calculating the heading, I can know whether it's pointing at the target or not. And it's going to be, if it's pointing exactly at the target, it's going to be a value of 1, this dot product operation. And if it's heading away, it's going to be further from 1. If it's completely perpendicular, it's going to be 0. And if it's opposite, it's going to be negative values. So that's how I can tell that whether it's facing the right direction or not. And this is also something I use, if you see right here, to set a reward during the get observations method. So I test if the heading is negative, I set a negative reward, which is a penalty, meaning that the car is facing away from my target. I don't want that. So it's like bad car. You should be facing the other direction. I also have a function to get the current throttle for the car. That is going to be done by the actions sent back into the agent. But it could be basically what the current throttle for the car is. And I'm going to also set a penalty if there is very little throttle. This is to encourage the agent to step on it, to go faster. Because sometimes I test and I see that the car is not moving during the training phase, it's not moving as much as I want it to. So what I can do is I identify those situations and maybe add penalties to that. Then the agent will understand that it's not something that it needs to do, and then we'll try the opposite. Oh yeah, one thing that is important is that we need to define the size of the observations in the agent. Let's go back to Unity for a second and I'll show you that. So this is my agent. The moment you add a component that extends from agent, it will bring along this script component, behavior parameters. Behavior parameters sits alongside the agent, and we can define a few interesting things here. For example, we can define the name of the behavior. That this is important. It will be in some files later on when we run some training, so make it something clear and meaningful. And then we can define the vector observation size. And you see that my vector observation size here is 7. And the reason for this is because I'm making 3 observations. the position of the car, the position of the target, and I also observing the heading. The heading is a float, just a value. But you will notice that the first two are vector 3, meaning that they take three spaces. And that's 3 plus 3 is 6, plus the float is 7. So that's the number that I define here, the size of the observations. In this case, I will encourage you to look always at the console and look for warnings, because in the past, if I'm calling and adding more observations than I have space defined for, it will say that there is a difference there, or that is truncated, so it's I'm losing on some observations. So it's important for you to set the right size, and always look at the console for any comments on that. Then we need to define the actions. So the actions are going to be what the agent can do. In our case, I originally defined steering and accelerating and braking. So, and I thought I can make the steering be a float from -1 to 1, 0 meaning not going anywhere with the steering wheel in the center. But when I tried doing that, in order to do so, we can test floats. That's using continuous actions. Continuous actions are of type float, and discrete ones are of type integer. So it turns out, of course, that the training agents with integer or discrete branches for the actions, it's faster, even though it's not as granular, but you can still add some sort of buffers on that will interpolate the position. But for the steering, means it will steer exactly all the way to the end or not steer at all. But it's very similar to what it's like playing with the keyboard instead of an analog that you can push the stick halfway through. So I originally wanted to try and train using continuous values, but it was taking too long. So I changed it to discrete. And then you can define how many types of actions you want to have in your behavior parameters. In my case, I defined 2. One is going to be for the acceleration. That I'll show you how I implemented this. Originally, it was going to be one for accelerate and brake, but that means that the agent could at any point like accelerate and brake at the same time, and I didn't want to do that. And we also implemented a way to, when the car is standing still, if we press on the brake button, the car will go backwards. So I wanted to prevent the car to going backwards, because I was seeing that behavior a lot. So I could have given a negative reward, but I tried instead getting rid of the brake button. So the car can only accelerate at different levels that I'm going to show you right now. And the next, the second branch that has size of 3, that is to define left, center, and right positions for the steering wheel. But then those actions, in order to see them in the agent script, we need to go and find them in the actions. Let me make it bigger for you to see. Let's look for actions right here, actions received. So by overriding and implementing this method on actions received on our specialized agent, we can test the actions from the receiver parameter type action buffers. And then there's properties such as discrete actions, which are the integers as we define, or continuous actions, which I was using originally. So you can see how I commented out. I decided not to use it. And I originally was passing 3 values. Because I'm going as many values as I receive, I'm going to get different value indices. So starting from 0, it could be 0, 1, or 2. And then I can assign whatever values I see fit those are. So for example, I can say for the first element of for index 0, I'm going to define that steer is going to be negative. So going back, I started from the second element of the array, discrete actions sub 1, meaning the one I define below here with a space of 3. So it's going to have the 0, 1, and 3. 0, 1, and 2. So as I said before, the steer is going to be -1, 0, or 1. These are possibilities. And then this one is testing the discrete action sub-0, meaning the first element, which is reserved for the throttle. And in my case, as you can see here in the editor behind, it says size 2, right? So this one is going to have 2 possible values. And I originally had a size of 3, giving it the option to go full throttle, but I ended up discarding that. I just didn't remove this case switch here. So the values that I can get from discrete actions on this function are going to be either 0 or 1. And I'm going to translate those in my own choice of throttle. It's going to be if I receive a 0, I'm going to set the throttle to 0.1. And if I receive the value 1, I'm going to set the throttle to like halfway. I don't want the car to go too fast. And this is something that is very important in machine learning, which is very similar to the way we learn. We should start slow. Because at first I was trying to train an agent in the most difficult situation, going at the fastest speed, and it's going to take longer. So it can happen, but it makes much more sense always to train in simpler environments first, having the car go slow, for example, in simple situations. So all I want to train my character to do is to aim towards the target first. So that is an actions received, and I also showed you the collect observations. So once I have these two, let me show you something more here in the behavior parameters. So model, I'm going to show you this later. Inference type, also I'll show you later. This is just to define what device to use. Let's just leave it as default. And behavior type. Behavior type is where we define how is this agent going to do the read the actions from. So default is set so that when connected to the Python API, it will actually do it through the Python API and go to the Python trainer, sending the observations. Then the trainer will decide on some actions and send it back to Unity, and then it will fit into the agent, defining the steering and the acceleration. Heuristics, this is what I want to show you next. If I set heuristics, this is to define a local solution for our problem. So we're going to provide the actions. If I go back to the code and look for heuristics here. So you can override the method heuristic, and I'm going to receive an action buffers. We're going to get like discrete, the discrete actions, or continuous. So we could here override the steer properties in this heuristic function that is going to be called, in case that we set the behavior type to use heuristic. So you see I added a comment here, and this is going back to the previous webinar where we discussed input manager. So I left it empty here because this is taken care of by linking the input system with the car controller on awake. So we can have a quick look on the awake function, and this is what it looks like. This is the original system that we use in the webinar to define input system, where we do dependency injection on the car controller, where we have provided for acceleration, braking, and steering. And in that case, in the original case, I was linking it to the input manager read value method. And that's what I'm going to do for heuristics only. But you see the default case, which is trained by the Python package, ML Agents Python package, or Inference only, which we'll get into soon. It's using actually these local functions, get throttle and get brake. And what these do, if we go real quick to see to the definition, they just return this float value called throttle. And throttle is actually stored and defined here, as I showed you before, on actions received. So when the trainer sends back actions, sending a decision of whether to step on the accelerator or to steer left or right, is going to be stored in one of these floats. And then in the case I'm using heuristics, I don't go through there. I instead read the values from from the input, player input, as we used to do originally. And also this is a way for us to test that our system is working. We go back to Unity. And by inheriting from agent, you see that there's also a max step set to 1000. Originally it's 0, meaning that it won't never end. But I set it to 1000 in case that when the agent is trying to drive and try to get to the target, it will learn over time to get to the target, but at first it will try and go in circles or go drive far away. And then this is not useful in this situation. So we need to add a max step, or basically it's like a timeout. So if it doesn't reach the target in the given amount of steps, it will end the episode automatically. So by setting it to heuristic only, I should be able now to enter play mode. Now in play mode, I can use the going back to use my keyboard camera. So you can see that I'm driving the car around, and also you can see these debug lines that I created. So one is showing the car forward in green, and in red is showing the car to target vector. And then remember the heading that I mentioned last time. So if these two are aligned, it's going to have a value of 1. If it's perpendicular, it's going to be 0. And if I look away, it's going to be -1. So that's how I know whether the car is heading in the right direction. And that is one of the observations that I feed into the agent. And finally, when I touch the target, let's go and see what that does. You can see that the car resets. So I have, let's look at the steering target right here. So I added a little script that has on trigger enter, it will invoke this event on player enter. And if I find references where this is used, I can see that the steer to target agent, the class we were looking at just now, on enable and on disable, I subscribe and unsubscribe. And the handler that I decided for this, handle player enter checkpoint, will set the reward to 1. It's like a sizable reward, and I'm going to end the episode, meaning that I'm gonna tell the agent, you did it, you achieved your objective of reaching the checkpoint, the target. And then I'm going to call end episode on the agent, and this will cause the episode to be ended and restarted. And then this function is called, this method is called on episode begin. And on episode begin, I take the opportunity to reset the car and reset the steering target controller, which is the sphere. And all I'm doing in this case is I'm just like setting a random position and random location for the car. And for the sphere, it's just a random position. And that's how that's why you see both the car and the sphere jumping around within the range of the original position they were whenever I reach the destination. So this is what I want the agent to learn to do. So I started facing away, so it should learn to make a U-turn and face the sphere. Oh, it's even hard for me to get there. And that's it, and reach more and more. And there's many episodes and so on. So this is running the agent in heuristic mode. So now the important thing, I want to start training my agent using ML Agents Learn Python package. How do we do that? So first, let's open the window explorer in our project. Remember, we need to activate the virtual environment for Python. So that is on my env scripts activate. Now it's active. And here is where I can start my training by calling ML Agents -learn. And by doing that and press enter, you will see a beautiful ASCII art version of the Unity logo and this message right here that says start training by pressing the play button in the Unity editor. So remember I set the behavior type to heuristic, so I'm going to set it back to default. And this way it will connect. It will try to connect to the Python application. When I press play now, you can see training starts. So basically what this is doing is the Python package is sending observations to Unity, and that's how that's telling the car to drive, giving it steering information and throttle information. At the same time, from Unity, our driver agent is taking up these observations, like the position of the sphere, position of the car, and the heading value, whether we're heading in the right direction or not, and sending that back to the training. And this is a complete loop going back and forth, back and forth. And this is to speed up training, because similar to having a real person learn something, that it will take time. If we can speed up time, of course it's going to be better, because then we can have we can learn faster, right? So right now our car has been training for a while. I'm going to exit play mode and look at the console. The terminal says learning was interrupted. So now I generated some training information. If I go back again to the project window, in my virtual environment folder, I have a results folder. I already trained before, so there should be more results. Yes, and you're gonna see how many runs I did in the past. I think you can pause and resume the training on the same progress that you made, so that you can keep making progress. However, you need to make sure that you don't change the dimensions of the vector size or the different actions, because they will change the structure of the brain. However, if you just want to keep improving on it and have it run more sessions, that's fine. You can stop and then resume. So there is a resume function for that. So how do we do that? How do we train? So I like to open the console this way, going into my assets and showing Explorer to bring up the Explorer window in the project folder. And remember where we had the environment set for Python. So I can go into the Python folder, my environment. And what I like to do here is type CMD on the address bar here. Click, and it will open the Windows terminal in that folder. And remember, there is a script folder here, and there is an activate batch file that I can invoke, and that will start my environment. So from here, all I need to do to start training is called ML Agents-Learn. The first time this will work, but subsequent times I trained before. So if I try to call it right now, you will see an error, because I already used up the default results folder. So it's always a good idea to give it a name. So in order to do that, we can do the following. I just type ML Agents-Learn, and then there's this parameter run ID, run ID equals, and give it a name. So I'm going to start from, I'm going to give it a name called run_100 and press enter. So you see the beautiful Unity logo in ASCII. And you see this line right here is important. It says listening on port 5004 and start training by pressing the play button in the Unity editor. And now in Unity, back in Unity, I need to make sure that, remember, as I was playing just now in heuristic mode, right? So I need to set it back to default. This way it will connect to the Python trainer. And when I enter play mode, you see some information show up on the right side, and on the editor itself, you can see the agent is driving on its own. I can show you, I'm not doing anything. It's running on its own. Here you can see some of the information regarding the training and how it's doing. And over time, there is a line that shows up in the console saying how many steps. There's like a checkpoint. Every so many episodes has training steps. And there is like a line of progress showing also like what's the mean reward for the agent. And that over time is going to improve. Also the time it took to resolve each iteration, that we expect it to be shorter and shorter every time. Let's let it train for a second, and maybe now we can stop play mode and see what happens. So if we look at the console, it says exported the results into this folder. Results run 100, which is the name I gave it. And there's a steering folder, and this is ONNX file. That's an Open Neural Network Exchange format, and that is the a trained model. So we didn't train it enough, so I don't think it's a very good one, but that's where it's stored. So imagine that we have to close the computer and we need to resume training another day. We can do so. We can start a new training by giving it a new run ID, like 101, or you can give it the same one, but then mark it as resume. And then by doing that, it will continue improving the already trained model that we had. And if I do that, I can click play and continue training my model from where we were. If I exit play mode, you see that it overrides the same file, run 100. And this is good so that we can keep improving our agent. So one thing also that you can do is bring a configuration file. So every time you run training, you see all this information here in the console. Some of these are parameters by default values, or some of the things that we define ourselves, like for example, the name of the run. It's given in the command line. However, you can, after you've done a run, you will find the config file generated with some of this information. So if I open my environments, results, run 100, you will find this configuration YAML file. So what I like to do is use this configuration file directly when I run the machine learning. And if I open it with the text editor, I can see all the values that it's using, including the run ID. So another thing that I can do is this resume true. Oh, it's already set to true because when I run this from the console, I set it to resume, right there. So that's why also it's in the config file. This means that I can just reuse this config file for my runs. So I could actually just run it directly from there. Let's try and do that. So it would be ML agent, ML agents learn, and then I can just specify the name of the config file, which in my case, it will be inside results run 100 or 101, yeah, no, 100 configuration.yaml. So it's the file that we saw before. If I run this, I no longer need to specify the name ID and resume flags. These are all being read from the YAML configuration file. So I can just continue training from here. And in the future, if I want to change some parameters for this particular training session, I can edit the YAML file and change any value there and call this line only. Just ML agents learn and then the configuration file. Another thing I wanted to show you is like, for example, this thing right here. Summary frequency right now is set to 50,000. I think that's a bit too much, so I can increase that. So let's exit play mode for a second, go back to our configuration file and the summary frequency here. Let's set it to 1000 just for this purpose. And this is important as well, maximum steps, 500,000. Apparently that is a good measure. But I managed to reach that limit after 1 or 2 hours, I think, of training in one agent, and it still wasn't performing to my expectations. So knowing this, I can go back to the configuration file and increase this. I can add a 0 and have it go up to 5 million iterations. So save that. Summary frequency every 1000 and increase the max step to 5 million. Maybe a bit excessive, but we'll see. Let's try again. So I just ran the same line and it's going to pick up my new values from the YAML configuration file. So it's listening on that port. I can click play and look at the information here. Now it says summary frequency every 1000. And it says resuming training from the step that it reached last time was 7000. So you see how by having changed this frequency value, now we got a line. That's a step 8000. It tells me how many seconds it took, what is the mean reward for all the attempts so far, and that is training. So here we can see some of the progress being made. This is typical that over time there will be the time taken, time elapsed will be reduced, meaning that the agent will achieve the goal much faster as it gets smarter and learns how to perform the operations. Now I want to show you the ability for the system to train multiple agents at the same time to improve and make this faster even. So I already created and duplicated sets of these characters, this pair of a car and target in an environment. So I have a target, the car, and the agent is just a simple game object with the agent script. But I put them inside one game object, and I duplicated this many times. So I can show you what this looks like by re-enabling them. They are all around this big plane. So let me zoom out a bit. So here's where you find the other pair of car and checkpoints that I distributed quite far away from each other, just for them not to bump into each other. And having done that, I can just confirm for a second that the other driver agents are set to default. That's correct. So if I go to my console and run the train configuration again, it will say waiting for and enter play mode. So now I have many agents training at the same time. And you can see now that the frequency is much faster. And this is how you can train multiple agents at the same time. Okay, finally, let's have a look at one of the brains that I trained for the longest time in my attempts. Yesterday, I left it training for quite a bit of time. And then by calling this, I should resume the session for run 046, which has quite a lot of iterations on. Press play. And now you can see it's quite good. If we go back to the console and look at the values. So I trained it for how many? 4 million. 4 million steps. So you see how I changed my maximum steps to 5 million. I thought it was excessive, but I actually reached that. I think in a matter of hours, maybe 3-4 hours. I don't remember exactly. I might have left my computer unattended while training, and then I came back and it had made some progress. So the good thing about this is you can, if you want, you can improve your agent model in different settings. So you can make it smarter over time. And in this case, actually, I realized it is still not exactly what I wanted it to be, but it's not too bad. I mean, it's reaching it's struggling. One of the reasons is because the car controller is the car is very slippery. So even humans driving this for the first time will have a tough time. So actually, I think if I train it some more, it will probably improve to the point that it will be even better than humans. But this is the state of the agent as I have it right now, trained to go to a checkpoint. So the idea of doing this is so that in the future, when this model is accurate and then it will aim correctly to the checkpoint that I want it to go, in the actual racetracks, I will have a set of checkpoints laid out throughout the scene. And then that will cause upon reaching a point where the next checkpoint is where the car should steer towards, that will be the target. That will be the target set for the agent. And then the agent will be able to go to that target. And once it reaches the next one, it will try to aim for the next, so that it will stay within the track. And I'm going to stop training for now. Let's have a quick look at the console. So this one is also, I'm actually just running one agent, so I could run multiple to improve the speed of this. But now actually reward is positive. It's on the positive side, you see. This depends on how you define your rewards in your agent logic. But it's interesting to see the values change. There's also one additional tool that you can use to visualize these numbers better and historic values as well. It's called Tensor Board. In order to use it, we just need to bring up another console like this one right here in the same and activate the virtual environment for Python. So I just go into the same environment folder and type cmd. Then I proceed to go into scripts activate to activate the virtual environment. And here I have a line that I'm going to paste here that reads TensorBoard -- logdir results and run it. When I run this, it says right here that TensorBoard is running on this address. It's like starting a local web server. I can copy this address and put it into a browser to see what it looks like. And this is what it looks like. It's actually reading that results folder that we saw before. And for example, the one that has like 5 million iterations, let's have a look at that one. That is 46. Toggle all, sorry, here. Very simple. Okay. The reward chart is a bit flat. This one doesn't really give me a lot of information, but I think here there's one that is promising. I can see the episode length, how long it takes for the agent to complete an episode. So the maximum would be probably the timeout that we define. But as you see, as time progresses and we're getting close to 5 million training episodes, the time to the episode length improves. So it becomes smaller, meaning that it's actually showing some improvement and it's getting to the checkpoint by its own. And that is TensorBoard, a way to visualize the results. And that is how we train agents in Unity. This is the second checkpoint. Let's see if there's any more questions at this point. Okay, so I'm going to go have a look at the questions and answers. There have been a lot of questions coming in and we have been answering some of them. There's still some in the box right now. I'm going to have a quick look. So, okay, there's one that says, does ML agents only use only one type of neural networks, or is it compatible with different kinds of neural networks? If so, how can we use those neural networks to be implemented? So my understanding is that, as I mentioned before, it's based on this ONNX format, but that is a very standard format for neural networks, which I understand other neural networks can be converted into. And there's been talks about people wanting to use the Python side, the training side, and not Unity to pass observations and have the agent separately, or have Unity connect to another trainer that is not based on Python. And those are all possible scenarios. They are covered in the website where the open source project is in GitHub. So please have a look there to get more information. But basically, the quick answer that I know right now is that it only uses the ONNX. Next up. It says, can you update the reward system while maintaining the current brain model? Yes, good question. I tried this before and it does work. And it's very similar. Training is very similar to like real life. Imagine that the scenario of sending your kid to school, and after 1 week or 2 weeks, there's a new teacher. So the kid is going to be the same and is going to have to learn something up until this point. But then the new teacher has a different teaching style that will reward different behaviors, and that will build on top of the experience that the agent had at that point. So that's a good question and it's a possibility. And you can do this, and it's exactly one of the approaches called curriculum learning, which makes sense for real life as well, where the case is if you want to teach someone to run and jump, for example, the first thing that you need to learn is how to walk. So you can have the model trained to the point that they can walk well, and only at that point start training them on how to run. And then they will do much better. It's very similar to real life. They will learn much better to run if they know how to walk to begin with. You can also start from scratch and try to get an agent to learn to run from scratch. But then that will take much longer because they don't have the foundation. So it's very, very good question. Let's see if there's another one. Yes, here. Can we use ML agents for games in production? Is there yet? Yes, there are games, and actually later on I'm going to show examples of games that are using ML agents. This is a new topic and is for experimental situations usually, but not necessarily. It's more for expression of movement. You will see that in simulation, often you will see how they train an agent to walk, for example, and it's a biped or we have a dog character that we'll see later on in the presentation. That it's basically like a ragdoll with physical limbs attached to it, and it will learn that in order to move from one point to another, it has to learn to stand and take steps. And that is emergent behavior based on the training that allows the character to find how to move around by himself. And some of these behaviors are used in some games that we show later on. There's an example of that coming up. And let's take one more. Answer live. Can we not train multiple car agents without bumping into each other? Yeah, there is. So right now, as I said, you start from the basics. And in my first attempt, what I wanted to do is have the character, the driver, the car be able to steer in the direction of a checkpoint. Once the agent knows how to do that properly, then I'm going to start making it go around the track by moving the checkpoints in front of the driver. And then the following thing to do will be to train them on avoiding obstacles. And by having multiple versions of the agents running around the track, instead of like driving through each other, clipping through each other, they can be trained to observe the position of other players. And then, for example, when they bump into each other, they can get a penalty, like a negative reward. So that would be a way to go about doing that. And I think we are going to move on. There's additional Q&A at the end of the presentation, which is a few. So that's the last part of the presentation. Let's continue with the presentation. Finally, after having trained our agents, we can then proceed to embed the trained model into our application. Let's have a look. Okay, so I showed you how to train your model. Then how do we use it? How do we embed it into the application to use it for a game, for example? So in case we want to do that, we need to go back to the folder where we created the neural network file and look for it. You go to Assets, Show in Explorer, go inside the virtual environment folder that you created, and the results folder. So I'm interested in using I think it was run 46, the better one. Let me have a quick look at my notes to see if that's the correct one. Yes, 46. All right, so 46. Here it is, steering ONNX. It's Open Neural Network Exchange Format. It's a bit like a FBX for neural networks. And you can see that it's actually quite all right in file size. It's like just 74 kilobytes. Once we locate this file in the results folder, we can copy it and bring it over to the assets folder in our Unity project. I created a folder that I like called brains. So I'm gonna drop it here. And I already had a previous version. I'm going to override it because I improved it a little bit just now, right? So I'm going to replace it with a newer version. Just make sure you do this in the Windows Explorer and not in Unity. Otherwise, Unity will create a new file alongside this one instead of overwriting it. And then we can look at it in the project window. So in the brains, we have steering. And if you look at the inspector on the right side, quite a lot of features corresponding to this file. Okay, now that we have the neural network file brought it into the project, and I'm going to show you the rest of the properties in the behavior parameters component. So if you have a look right here, remember the behavior type was set to default, so it will connect to the trainer. And if I select inference only, then I expect it to define a model right here in the inspector. There's a slot for model. So if I open this one, I will find the one I'm interested in, which is steering. So by setting that there, and I don't have the Python virtual environment running or anything like that. I just have Unity with my model, which is a baked brain that I trained for hours. And now I can enter play mode, and in real time I see my agent driving around and taking decisions, trying to get to the target. I think it's struggling a bit. I think it's not gonna make it, but it's trying. I assure it's trying. That I think the max step count is still counts even if it's in red for the model. So I can make that 0 so that it won't ever stop. The episode won't end and get restarted. So by the way, when using the agent in production with a trained model, you should remove all the max step, of course, and there's no need to set rewards. I mean, I think those are probably ignored in this case. The only thing that is important for the actual agent that is going to drive using the model that we trained before is going to be the receive actions. That's and take the observations. Sorry, take the observations, which are sent into the model, the brain that we baked earlier, and through the Unity Inference engine, it will resolve and take an action offline, so it doesn't need to be connected to Python. So now this model, I can bake it and make, for example, an Android application or a PC standalone application. There are many platforms supported by the Unity Inference engine. And that is how you use a model that we trained for hours in our agent to make it smart. Maybe not so smart. To be fair, this car is very hard to control. So I think it's doing a great job. Sometimes it does some fun things like these donuts. And let me see if I can bring up also my initial attempt to train the car to drive around the original Laguna Seca track that we prepared earlier. Let's have a look. So here I have my driver agent set to, let's set the behavior to inference only, and let's set the driving brain to it, and that's it. Let's enter play mode and have a look at how my amazing agent drives around Laguna Seca. He's not doing too bad. I think I trained him for a while. Okay. So in this is the particular case where I had set my actions to be continuous actions. So I was being ambitious, like using float values from -1 to 1 to control the steering, meaning that it could be gradual. And then I was using positive values to dictate throttle and negatives to dictate braking. And that's how I read throttle and brake. But as you can see, even after training for a long time, my particular car is not driving very well. But you can see my strategy for this one is I was again getting the heading for the car, and I have a checkpoint system that is laid out as triggers around the scene, as well as you see on top there, like there is some rays in red color. I didn't show you this, but there is a way to add sensors that come with the ML Agents Toolkit. This one is called Ray Perception Sensor 3D. I added it as a child of the driver agent, and you can specify how many rays, in what angle, what spread, using a sphere cast, or if you make the sphere very small, you use like a ray cast. This is kind of giving the car a sense of like perception. Imagine like driving a toy car and putting your fingers in front of the car to feel around the surface that the car is driving on. That way, if it hits anything, you can specify what are the ray layer mask, what are considered obstacles. Then that information, the vector information, will be fed into the neural network for training, on top of the observations that I defined to set. Here we go. I want to show you the checkpoint system real quick. That was part of my strategy. And also probably the vectors. I put them way up there and not in front of the car because this particular training environment is also very challenging because there's a lot of elevations. So when going uphill or downhill, I want to be able to see. So actually, my strategy for this is the agent that has the position where the sensors are going to be cast from it's got set position and rotation constraint that are tied to different things. So this is not the best example because I'm relying on the camera, meaning that if I have multiple agents to train in parallel, it's going to be a challenge. But I wanted the agent to have a sense of the same sort of perspective as the player will have in the end. So yeah, that's why I wanted to focus on front, to be in front of this, basically in front of the car. Even if the car is did a donut and it's facing me in the camera, the ray casts are cast from my point of view of the camera. That's why I'm rotating the driver agent, which is casting the rays, always forward. And the position constraint is so that it will follow the car. Sorry, before I enter play mode, I want to change to heuristics so I can have control of the car and show you what this looks like. Ideally, in my ideal scenario. So you see the green line shows the direction, the relative direction where I would like the car to go. The red line is identifying the velocity of the rigid body of the car at any point, which is interesting. Is different from the heading of the car, which is the forward of the car, because when the car is drifting, the forward might be sideways, but the actual velocity is pointing in the direction that the car is moving. So that would be the red line, and the green is the direction that it has to go to in order to enter and find the next checkpoint, which is in this corner. After I find it, it's going to say, okay, now go to the next one, and so on. And the idea was for me to feed this information to the training system and have it understand that it needs to drive around the track this way. But even after many attempts, I guess my other concern is that I can only train one agent at a time with this approach that I have here, meaning that I couldn't let it train fast enough to get a decent result. But you can see my intentions were good, how I have the sensor sensing the area. You can define different tags. I set penalties when the car crashes into an obstacle. In that case, I haven't set already I think I have a maximum. The timeout happened 10,000 steps. I remember I need to set this to 0 if I'm going to. Or actually, no, sorry. I think I have the crashing into an obstacle. Yeah, crashing into an obstacle will, during the training phase, what I was doing is setting a negative reward, a penalty, and ending the episode. So I didn't want the car to keep training after that. But there's a lot of work to be done to prepare a training environment. Again, probably this is the very complex environment and with a very complex and specific, like advanced car controller with a lot of features. In order to train this successfully to drive an autonomous way, we probably need to define better observations. I need to define better observations and train it, spend more time training it properly. But the idea, you see the green line changing there, that's what I wanted to achieve. Have the agent reason that it needs to bring the heading of the car in line with the green line. Because what I did in my code is, like, at that point when they are like almost aligned, I set a reward, a positive reward, and then when it's away, it's probably could be a penalty. Then my intention was for the car to learn that it has to face in that direction, therefore drive in that direction. But there's more to do. Like I can also I could also work on having the sides, the obstacles on the sides have different meanings to the car, or maybe the raycast. This is a off-the-shelf solution that I placed there, and I can define how many rays to cast. But there's not a lot of things that can be done with that information. in order to decide whether that is a good thing or a bad thing. It's just simply more information that the neural network gets, which is good. The more information the system has, the better. But that means that it will, if we don't give it a meaning, like for example, the rock should be considered something that is bad. Therefore, if it's getting too close, it should set a penalty to the agent so that it learns to avoid it in time. This one, so far, all it's doing is basically just detecting the proximity that is being fed into the neural network. And we have the ability to set different tags and also like filter by layers, of course, but they are all on the same layer, but have different tags, for example. And that could be a way to help the situation. Another approach that I've seen done in other cases is to lay out like invisible walls around the area and call that obstacles, put in an obstacle layer. The main camera won't render it, but the raycast will see it, and then the car will try to avoid, or yeah, we'll learn that those are there and we'll try to avoid them. But I think I need to train longer. My particular model that I have here is not trained enough to learn the difference. And the checkpoint system is somewhere here. This is what they look like. There's a bunch of boxes laid out. This is the trickiest one. But you've seen it, right? The moment I enter one of these triggers, the orientation for this checkpoint will decide the orientation that I hope the car was going to go for, because I'm feeding that as an observation to the agent. But I don't think I managed to train it long enough. But at least I wanted to show you that I tried. This is a good example of how we need to define very good virtual environments, training environments, and not just like go try to train in the final environment where the agent is supposed to work in. And very very much like in real life, it's like starting from the advanced level. You want to start from the tutorial, the beginning, the first few levels, and then have a user learn the skills. And once they learn the skills, then move on to harder and harder difficulties. Eventually, they will get to it. And that's something that can be done using the same model, continuing training on the same model, but changing the environment from like beginner to intermediate and then advanced environments, more challenging. And that is how we embed trained models into your application. Here's an example of a 3D character built where the limbs are attached to a physical object controlled by the physics engine, similar to a ragdoll. It has been trained to move from point A to B, and in that training process, the character learned to walk. There are no human-generated animations playing on this character. It's worth mentioning that embedding this trained character makes use of the Unity Inference engine, which is well optimized to run real-time and perform inference on multiple agents at the same time, even on mobile phones. Another example of ML agents used in games. Here, the developers of Source of Madness made use of ML agents to train their monster characters. You can see how they used the ML agents to animate the movement of these characters so that they look very organic. Similar to the 3D character that we saw before, this is in a 2D game. You can see how they train their characters by attaching these physically controlled limbs and allowing them to move and try to apply forces to the limbs attached to the bodies with the objective of moving from one point to another. And over time, during training, they learn the optimal way of pushing and moving the limbs to move the character as a whole to another position. And that's how they learn and they reach this position. Another thing that you can see the reward, how in these two examples, let me replay this real quick. The one on the left, the reward is to stay close to the ground. That's why you get the behavior of like rolling and dragging through around the ground. And the second one, there is a reward when they reach a high position, meaning that they will try to jump. They learn to jump because that's how they get the reward. And that's a way of like changing the reward system to get different behaviors. These are some of the examples of different types of learning environments that come with ML Agents Toolkit for you to explore. Here you can find how other algorithms and training methods are used. For example, you have curiosity that allows the agents to perform tasks that are not necessarily related to achieving their target objective, which is, for example, there is this environment where there is a pyramid, this one right here, where the agent is trying to find an item that is on the top of a pyramid of items, but it's on a maze. So the first thing that the character needs to do is actually go around the maze, trying to explore the maze and try to do something. When the agent knocks over the tower, then the item falls down and then it can pick it up. And that's what gives the reward. But without the curiosity, the agent will never try to explore the maze, or it will take much longer to train because it will have to try many different things before it achieves that conclusion. Then also we have memory enhanced agents that learn and remember things to use. An example right here where a character sees something and then when it's confronted with options, it will choose to go into the option that he's seen before. Concurrent Unity instances. Oh yeah, we can train by compiling a Unity build. It doesn't have to be running from the editor. So we can make a build and we can have training running off the build. And the ML Agents Python system allows you to launch multiple instances of a Unity application in order to train faster. GPU training as well, it's supported. I haven't tried it, but there is a way to define a CPU, a GPU, or even multiple GPUs if your system allows for that. And then the last two, pre-training and Gale, those are related to imitation learning, which is supported by the system. And it's something that allows the user to record a session to guide the agent. So that it doesn't have to try everything on its own by doing reinforcement learning and trying all the different elements and wait for rewards, but also has an example of maybe a human play session to compare against and then guide. This is also similar to the curiosity approach, where we can have a human explore the maze, for example, and then by training again using Gale, imitation learning, it will try to mimic the user's behavior, and that will allow it to get the reward. So it's a combination of rewards and imitation that allow the agent to learn faster. Here's where you can find some resources and sample projects. Is the Unity ML Agents project that we were talking about. It's on GitHub, and there's a lot of documentation explaining many elements on how to use it and how to train different scenarios. Very comprehensive, very interesting, fascinating topics to learn if you're interested in this. And finally, there's also a couple of videos that I recommend from Unite Copenhagen, and then another one showing a similar approach to what we're doing today, like learning how to create an agent and to allow it to drive cars around a track. Then I usually like to end my presentation with this quote, but instead of the usual one from our CEO, I wanted to share this next one with you. So in the 1984 movie, The Karate Kid, Mr. Miyagi said this phrase, and it's something that came to my mind often while I was staring at my screen during training sessions, trying to figure out if I laid out the learning environment correctly, or if I was providing the right set of observations for my agent/student. So it's something to keep in mind, as training intelligent agents does take a bit of time. So one could argue that our role as developers dealing with machine learning is that of a teacher. And with that, we've reached the end of our presentation. Thank you so much for taking the time to tune in, and I hope it has been helpful to you. And now we're open for questions. Thank you again, everyone, for staying online for the presentation till the very end. And I'm going to go and check if there's any more questions left in the questions and answers box. I have a couple that I marked to answer online. It says, Can we get the sample project for that you're using working on this session? Yes, I didn't prepare it just now, but I should be able to get that ready for you to be shared later on via email in the follow-up email that you get after the presentation. So I will package up a zip file and make sure that I send that link over so that you can get this project as it is. And then another question is, can I use a rigid body for riding the car by defining different physics properties, such as mass, drag, angular drag, so on? Well, yes, there is a way of doing this, and actually Tech, my teammate, covered this in the physics section of the series, where he explains how the car is built to be driven by physics. And what you need to understand is that the agent will be trying to mimic a user or a player. So if you define a car that can be played by user input, like a steering left, right, accelerating, and braking, then those are the actions that the agent must understand and try to apply on the same controller. And that's how you can train an agent. So you have to first get an agent that can be driven by heuristics. As we mentioned during the presentation, if the behavior type is set to heuristics, it will try to call that method in your agent specialized class. And that's with the opportunity for you to define control via input, like a keyboard input or mouse or whatever, game controller, whatever you're using, to try to control your agent, making sure that if the agent performs actions that should cause penalties, those happen. And the same way, if they perform actions which are like what a trainer intended, they will get a reward. And once you test that via heuristics, then you can hook up the actions to the model and let it train. So the model will, the training exercise will keep sending controls back to the agent, and the agent will perform that what looks erratic at the beginning because it's trying all these different actions. And in time, it will learn that the actions that it was taking, they either give it a reward or a penalty. And that's how it will like mold itself, like change and become like the smart agent that it needs to be. And that's how the reinforcement learning works. Great. I think there's no more open questions on my side, but I've been having troubles with my questions and answer box. Keeps disconnecting. I don't have any more. I have a question that says thank you. Thank you. Thank you for coming.
On this note, we've just shared the survey link in the chat box, so please fill it in if you like a chance to win a Unity Swag Pack. In case you don't want to take any more questions, Hector, would you like to share today's best question as well?
Yes. Okay. So actually, the best question, I'm gonna leave it to my colleagues to decide, and I think they sent me one already. I'm gonna read it. It says, is the benefit of training multiple agents at the same time that all the information from each agent training is combined during the number of training steps and time required? Or is it so that you could set the individual agent with different values, faster, slower cars, or a drunk driver, for example, and train them all at the same time? So you do not need to set up a separate scene for agents and every vehicle type to train them. So this is a good question, because as we mentioned just now, we can train the same, like we can make clones of the same agent to be trained in parallel, which speeds up training, so they learn faster. But at the same time, remember, if you go back to the first few slides that we did in the presentation, you can be training multiple types of behavior at the same time in the same session. So we, in our presentation so far, we've been using just one behavior, training one behavior, the driving. But we could have driving drunk, for example, or driving pro, working around at the same time in the same city environment. So we can actually have one learned driver learn from a very mature model. And this also goes in line with questions about like how to use train models for different levels of difficulty. So as you train your model, and if you've seen in the example of the monsters in Source of Madness, they actually show that they can achieve different behaviors by setting different types of rewards. But actually, you can also take the brain as like a snapshot of the brain during training, like the fewer iterations. It could be like low-level monsters, and you can save a snapshot of the version of the brain at that point, and then keep training from that. It's like a save as, and keep training the copy until it becomes a bit better, and that could be like the medium-level enemy, and then again do a training of that to create the expert version, and then you have the snapshots of this training, and you can use them at the same time on different monsters in your game, running inference at the same time. So yeah, that's it. Sarah, I'll send you the name of the person is Michael Dean.
Awesome. Yeah, Michael, I've dropped you a message. So if you could just share your email address in the chat with us, I will follow up with you.
Oh, sorry. One more quick comment. I wanted to give a shout out to Deshan, who sent me a question about I think I was misusing one of the methods. Instead of using add reward, I was using set reward. Be careful with that. That might explain why I didn't get the expected results. Because set reward will set the absolute value of the reward, and add reward will move the reward up and down during the same episode, which makes more sense. So thank you for that clarification.
Great. So Hector, would you like to take any more questions? If not, we can wrap today's session up.
I think that's good. Thank you, Sarah.
All right.
Thank you everyone for joining.
Yep. Thank you everyone for joining. So thanks for joining us through the Building an Arcade Racer series. I've dropped the link to catch up on the past sessions in the chat, so you can view all the past recordings for this series. And this month we've just sent out the email for the upcoming webinar sessions, so you can look out for that. And if you haven't received the email, you can check out our social media pages as well, which is in the chat. So we will see you next week for our webinar sessions as